Good afternoon, everyone. It's my very great pleasure to welcome you here. So we're very fortunate to have Pierre Alquier as a speaker today. I've known Pierre for quite a while now. Actually, I think up to a couple of months, it's exactly 10 years that we've known each other. Pierre, yeah, feeling old, right? Pierre's done his PhD
I didn't know you were that old, actually.
You're older than me. So Pierre did his PhD in France with Olivier Catoni, and he was then a lecturer, or as we call it in France, maître de conférence, which sounds way cooler, in Paris. And then he moved to Dublin for a couple of years where he was a lecturer, and then back to Paris as a professor and is in Japan at Riken. He's been working on many topics, including back-Bayes, regret bounds, generalized Bayesian updates. Pierre has been a colleague, a mentor, a friend for the past decade. I'm very pleased to have him today. And he'll talk about regret bounds for generalized Bayes updates. Pierre, the floor is yours.
Okay, thank you very much, Benjamin, for these kind words and for the invitation. So indeed, actually, I'm going to talk about generalized Bayes in online framework. So which means that actually at some point I will derive some regret bounds. Maybe before announcing the main the roadmap of this talk, I will directly start by explaining what I'm going to do. So we will work in the sequential prediction problem. So you can imagine like sequential regression or sequential classification. So an object will be given, and then you have to try to predict the corresponding label. And then the true label is revealed, and you suffer the corresponding loss. And then based on this, you update your knowledge, you update your model, and then a new object is given, and you try to predict the corresponding label. And then once again, the true label is revealed, and so on and so on. So in this context, very often, instead of trying just to gather some data and to minimize the risk on the sample or something, the objective is to make sure that we learn to predict as soon as possible, so that each data that arrives brings some new information, and you update your knowledge so that the following data can be predicted better, actually. So the quantity that we want to keep small is the sum of the losses between your prediction and the true label. At time capital T, that might or not be known in advance. So actually, whenever you stop the game, you want to make sure that this sum is as small as possible. And I'm just going to present classical approaches, just as a reminder. And then I'm going to explain what are the approaches that I'm going to talk about more specifically under the name generalized Bayes. So assume that you have a set of predictors. So like as usual, okay, it can be anything. And I'm going to pretend that it's a neural network. But in practice, the results work mostly for linear and logistic regression. I'm exaggerating a little, but okay, it's any set of predictors for now. And you have for short, I will use like the notation LT of theta. It will be the loss when you use predictor theta on object xt to predict label yt. Okay. Basic strategy, actually, when I say basic, it's not basic because it's easy. It's not what I mean, but it's just that it's usually the first one that is introduced in most lecture notes, is to minimize the sum at time t. You try to, in order to predict yt. So say you have observed the data from time 1 to time t minus 1, and you want to predict the data at time t, okay? Then you minimize the sum of the losses between time 1 and t minus 1. Actually, if you just minimize the sum of the losses, you obtain something that is quite unstable, and that apart from a few special cases, does not work. But if you add some penalty with suitable properties, so I will denote this penalty by pen of theta, then you end up with a strategy that had been studied in general and that has very good properties. Okay, so I'm just going to specify the most famous instance actually of this general follow the regularized leader strategy. And it's just to choose the quadratic loss, for example. So which means that actually the set of predictors theta is a Euclidean space. You take the quadratic Euclidean norm, And then actually you linearize the losses in order to get something more explicit. And then actually you just want to minimize, so this sum of linearized losses plus the quadratic penalty. And of course, it can be solved explicitly. You differentiate this, and actually you see that theta t must be equal to minus the sum of the gradients that you have seen so far. Okay, and of course, like as the same relation holds for theta minus 1, that would be the sum from between s and t minus 2, then you can write the relation recursively in the following very famous form. Theta t is theta t minus 1 minus eta times the gradient on loss t minus 1 at theta minus 1, t minus 1. Okay, so this is very classical update, and it's been studied for years. And actually, if you want to learn about it, the best thing to do is to read some classical references. There are many good references, including these two books. I used them myself when I was teaching a lecture on the topic, and so this is where I learned actually most of the things I know about this. Now, another strategy that is, and probably Benjamin will share my opinion, that is also something very important, and that it's something quite well known. It's known under many different names, actually. So exponentially weighted aggregation, multiplicative weights, but also I will use the term generalized Bayes. So the idea is this time that you start with a prior pi of theta, and then at each time t, so once again, when I'm in time t, actually, I assume that I know the data only up to t minus 1, and I'm trying to use my knowledge to predict the tth observation, okay? So I will build a pseudo-posterior distribution in the following way. I multiply the prior by exponential of minus a temperature parameter, eta, times the sum of the losses so far, okay? So the thing is that I will spend some time on explaining some properties of this pseudo posterior, but here again it's something that is has been known for years and years. So as far as I remember, the first paper on this rule in the online case, actually it was called like multiplicative weights. It's from 90, no, it was actually aggregating strategies, but the term multiplicative rule was already used in the paper, and it's paper by Vogt in 1990. But if you think about it in Bayesian terms, in statistical terms, then actually it's much older than that, actually, and you see that it's a well-known principle. And here again, like very classical reference where many properties of this thing are derived. Now, actually, the thing is that it's well known that there is another form to reach this rho t. So this construction here is quite explicit. You just start from a prior and you say how to move the weights so that in the end you end up with a posterior that is concentrated around the relevant parameters, theta. But actually, from an optimization perspective, the following formula, even though it's less explicit, is also very useful. Actually, it's known that rho t can be seen as the minimizer, not of the sum of the losses as we had before, but of the sum of the expected losses where theta would be drawn from rho, okay? And plus a penalty, and this penalty is actually the Kullback-Leibler divergence between rho and the prior pi, still over a constant eta that we have to discuss later. So actually, up to a change of notation like we had before, small l, now we switch to capital L, which is the expectation. This is exactly a special case of the follow the regularized leader strategy. And so yeah, sorry, just with a special, of course, like a special case for the loss, because actually in this case you have a loss that is the expectation with respect to rho, which means that actually it's a loss that is linear with respect to rho. And then you have a special case for the penalty. It's the Kullback-Leibler divergence. The point is that this form is known in Bayesian statistics because very often when it's a bit complicated to sample from the posterior or to approximate it, sorry, or to exactly, sorry, when it's a bit complicated to have an idea of what the posterior looks like and to sample from it, then actually people like to come back to this form and to say, if we cannot find exactly the minimizer of this thing, maybe let's look at the minimizer on a smaller set, like for example, the minimizer on Gaussian distributions. This is what's called doing variational inference, and it leads often to tractable approximation of posteriors. So from now, I will focus on this generalized Bayes rule, but seen actually as this minimization program. And as we've seen before, that actually follow the regularized leader was studied with a general penalty, maybe we will actually switch to the general form in the pseudo-Bayesian version. So actually, it's a doubly generalized Bayes. It's generalized because here you don't have a likelihood, you have like simply a sum of losses. So it's kind of extension of the usual Bayes setting. But another generalization is that you don't minimize here with the KL penalty, but you minimize with more or less general divergence D. Okay, so the study of this, well, of course, I mean, there is a general study of follow the regularized leader that was done. So in some sense, it's a special case, even though actually it was, as far as I know, never written under this form, but it appears that it leads to some interesting properties. So this is covered in a recent paper that was accepted at ICML. And this is what I will study in the first time. So say 15 or 20 minutes, I will explain what is the minimizer of this quantity and what are the properties in terms of online prediction. In a second time, I will switch to a connection with an older paper with my former PhD student, Badreddin Shayef Abdelatif, and MT Khan, who is the leader of the team in Recon, where I work in now. So I will focus on the case where you constrain the minimization program here, to a smaller subset than the set of all probability distributions, so that you end up with something that is probably more feasible in practice. And I will provide a few theoretical and simulations results on this. So I just wanted to present, actually, to introduce my two co-authors on the second paper. Badreddin, so I told you my former PhD student, is now a postdoc in Oxford, and MT Khan is the leader of our team, approximate Bayesian inference team at Recon AIP. So you have the page of the team here. And these slides, by the way, are on my webpage, so you can access them if you want this information later. So now I can finally give you the schedule for the end of the talk, actually. So like 15, 20 minutes, I will cover the generalized Bayes update. So when you replace the KL by any divergence, I will obtain something that I find funny and nice, but maybe the practical consequence of this can be questioned, and we will focus on more practical algorithms in the second part, so online variational inference. Okay, so first, the generalized Bayes update. So as a reminder, just the definition of the update. So you try to build at each step a probability distribution that you will use on your parameter space. But it's not the posterior in the Bayesian sense. It's the minimizer of this sum of expectations, plus actually a divergence between rho and pi. And well, the results that I will present, at least some of them, require that the divergence has a special form. So that actually it's what is called a phi divergence or F divergence, depending on the papers. Which means that actually it has to be written in this way. Sorry, excuse me. The divergence is actually the expectation when theta is drawn from pi of phi, where phi is a function that has these properties, especially its convex function, of the density of rho with respect to pi. So which means that actually you assume that rho has a density with respect to pi, or that rho is absolutely continuous with respect to pi, which is what I mean by this symbol. If it's not the case, it's defined by as infinity. Okay, so you have some conditions on phi. You don't have to read everything because actually I'm sure that we will all forget, including me, actually, I will also forget these conditions in the next slide. But essentially, these conditions ensure that when I talk about things later, well, these things are actually well defined and unique. So you have the following conditions on phi. So two things, actually. First, I will derive, when it's possible, a more explicit formula for rho. And in the second time, I will study the properties of rho. So there is one tool, actually, that's necessary to derive the explicit formula for rho. It's the convex conjugate. So, and not exactly the convex conjugate of phi, but the convex conjugate of this phi restricted to the set of non-negative numbers. Like, in the sense, I define phi tilde as phi of x if x is non-negative, but plus infinity if x is negative. And then I define phi tilde star, as usual, as the convex conjugate as phi tilde, that is the supremum of xy minus phi tilde of x, the supremum on x, okay? And the point is that phi satisfying the previous properties and being differentiable and strictly convex, then actually phi tilde star, it's quite just a standard actually results from convex analysis that you will find in the introduction.
Yeah.
Yes?
Yeah, Pierre, sorry to interrupt. This is a phi tilde star of y, right? That you're evaluating.
Oh, I forgot the y here. Yes.
All right.
So,
okay. And yeah, so I'm just taking this excuse also to mention to everyone that if you do have a question, please type it in chat or unmute yourselves. Maybe that's fine.
Okay, so I mean, I'm absolutely not paying attention to all the pings on my screen. So if there is a question on the chat, just let me know. It's fine to interrupt me, but just do it because otherwise I will miss the
I'll
question.
let you know. No worries. Thanks. Carry on.
Yeah, it's a phi star tilde of y actually. And then actually this is differentiable, and it's quite actually easy to find the derivative of this function. It's gradients if you are in RD. Actually, yeah, y must be in RD. There are probably a few typos in these slides because it's the first time I give this talk. But then actually, it's in some sense what you do is that if you want to compute phi tilde star, well, you will differentiate xy minus phi tilde of x, and then you will try to find the x that reaches the supremum, that is that will make the differential equal to 0. And actually, this will correspond to the differential actually of this function. So actually, if usually when you compute, when you try to calculate by hand like phi tilde star, first you end up with the gradient and then you plug the value into phi tilde star. So anyway, what matters here is that when you have this function phi, you can build phi tilde, and then you can build its convex conjugate and the gradient of its convex conjugate. And this function, gradient of phi tilde star, is quite important because it appears that we have the following results. Don't read the first lines because I will read them later. Just read the last line. The posterior, that is the minimizer here of this quantity, is actually a function. It's still a function of the sum of the losses, but the function this time, instead of being the exponential function, is the gradient of phi tilde star, and it's still multiplied by the prior. Okay, there are two surprises. The first one is that you don't have here proportional to as you would have here. You know that here, here I wrote proportional to because of course you have to renormalize rho. Actually, it's not exactly how it works in general here. It's exactly equal to this quantity, but here you have a parameter lambda. And actually, it's the choice of this parameter lambda that will allow this to become a probability distribution. In some sense, there is only one lambda, and this is proven in the paper thanks to tools that come from earlier paper that I will mention in 1 minute. But it's proven in the paper that you have only one lambda. This lambda exists and is unique under the assumptions stated above, such that this will be a probability distribution. And another way to find this lambda is actually just to use this definition here, But I mean, if you just check this definition, you just differentiate what's inside this argmin, and then you see that actually lambda is the only one such that this will integrate to 1. So it's fine, actually. This is really what lambda is. Lambda is a normalization factor, but it's not a factor, actually. It's a factor only in the exponential case. Otherwise, it's a normalization thing. I don't have a better word for it. Well, I told you don't read the first line. The first line is actually just a few additional assumptions on phi so that actually everything is exists and is well defined. Technical assumptions. So I really needed these assumptions in the proof. Maybe it's possible to remove them, but as far as I know, I mean, until now, I was not able to remove these conditions. So
may I ask a question quickly?
Yes, of course.
So, well, hang on, can you go back a slide or is it forward a slide?
Oh, sorry.
Yeah. So is this important because lambda t is presumably easier to find than a normalization constant?
No, sorry, no.
Okay.
I said clearly in the beginning, like it will lead to a result that could be nice, but the practical, in my opinion, the practical importance of this result is not clear yet. And indeed, actually, if it's not exponential, then the normalization can be more difficult, actually, not easier.
Okay.
So I've been working with colleagues on a new project where we try to see like how is the computation of lambda t. Maybe in some cases we have some idea, but in general there is no reason for this to be easier than the normalization constant.
Okay. In that case, might as well you forget about this result and just try and normalize what you've got below without
here?
the lambda t.
Like
maybe I'm
replace
asking
lambda t,
confused question.
and instead try to normalize that.
Yeah, something like that. Does that make sense?
Why not? It's another definition. The point is that the theoretical result I will prove are for these objects and not for another normalization, actually. So
right. I understand now.
But I mean, once again, why not? And actually, it appears that I know a place where the object that you mentioned, that's just like forget about lambda t and instead normalize this. Actually, if you go to this book, at some point, it's in a very special case, they derive properties also of this. So it's probably possible to study it. I just want to cover two examples. The first example I take, so, like in the phi divergence, I take the function phi equal to x log x. And it's known actually that in this case, you obtain the Kullback-Leibler divergence. The point is that you can just check, like, so try to compute the convex conjugate of phi, and then actually it's just two lines. You end up with exponential of y minus 1. And it's nice because the gradient is also equal to exponential of y minus 1, which means that according to the previous theorem, rho t is given by this exponential of lambda t minus eta, the sum of the losses minus 1 times pi. And then you have to renormalize it. And you know that actually lambda is such that this is normalized. So in this case, as the exponential of the product of the sum is the product of the exponential, it means that you can immediately guess your lambda. It is such that rho is equal to the usual exponentially weighted aggregate or the usual pseudo posterior. So it's perfectly known, but well, I mean, when I found that, I was thinking, yeah, okay, at least it's nice. It means that maybe there is no mistake in the previous general results. Now, let us check another funny example, and maybe Benjamin will guess the form of the results, because we had a paper that was kind of looking like that, even though it was not exactly the same thing. Like in this case, I take phi of x is equal to x squared minus 1. And remember that phi tilde would be x squared minus 1 for a positive number, but it will be infinite for negative numbers. And then actually you just differentiate so that you can compute the convex conjugate. Is given by y2 over 4 indicator that y is non-negative. And then you differentiate to get the gradient of the convex conjugate. And you obtain y over 2 plus. By plus, I mean that the positive part, okay? So it's the maximum between what's into the parentheses, the brackets here, and 0, okay? And so here, it means that you end up with another posterior that's well, also a function of lambda t minus eta times the sum of the losses. But this time, instead of going through the exponential function, you go through the maximum between 0 and x function, okay? Well, I mean, it's in this case, for example, you can think about it. This is the example where we start to think about how to compute lambda t. It's possible to do some optimization procedure to get lambda t, but it's not maybe that intuitive what lambda t is in this context. But anyway, what's nice is that despite this, we have a more or less explicit formula for rho t. What I would like to do now is just to give a few references, because once I did that, I was like, wow, I like this formula, it's nice. And then obviously, like you start to talk about it and you realize that many people knew it already. A few papers provided like formulas like that, the general formula. Actually, this formula is almost exactly given in the paper by Mark Reed and co-authors in called 2015. Well, the main difference being that actually it's given in a finite parameter case. And in this case, well, the formula is the same actually, but it's just a finite parameter set. So if you want to extend the proof to the general case, you have to be a bit more careful about like the existence of some of the quantities. But essentially, this result was known in the finite case. I just want to mention that actually there are advanced convex analysis tools in the proof for the general case, but I don't say that to say that I did something complicated, because the most complicated I did was to find the right paper. Actually, a paper in ICML last year where many properties of F divergences are derived. And at some point, the author provides exactly some of the tools that are needed to extend, in some sense, the proof of Reed and co-authors to the general setting. Okay. I also want to mention that with Benjamin, we wrote a papers 2 or 3 years ago. This paper was not at all written in the online setting. It was written in a usual PAC setting. So with IID observations, which is an additional assumption. It's slightly different, but still we had some kind of PAC-based bound with the chi-square divergence. And moreover, even though it's not exactly the same, the posterior shares some similarity with this one. There's also a truncation actually at 0 at some point. So I wanted to mention this. Also, and I think like for me, it was the motivation for this work. Like many people start recently to try to generalize variational inference. So this formula here using something beyond the KL divergence, but maybe having a look at Renyi divergences or then phi divergences. So many other possible penalties. And actually in this paper by Jeremias Knobloch and co-authors, it's quite a long paper, but they provide many arguments in favor of these generalized pseudo-posteriors. I must say that some of these arguments are convincing. Maybe some other are less convincing. I think, of course, like it's a very nice paper and it's very challenging. This paper by Jeremias and co-authors. I talked actually with Jeremias a lot about it. Myself, I'm not actually convinced now that I would use this in practice, but still. I'm convinced that at least it's an interesting object from a theoretical point of view because of a property that I'm going to derive now. So I'm going to give now the regret analysis of this. And
Pierre, sorry, yeah. Before you jump in on the analysis, I do have one question regarding eta.
Yes.
So yeah, exactly. So eta doesn't depend on t, but morally you would like eta to also reflect. Because in your variational objective, I guess there's a hope that you could penalize the phi divergence also with respect to time, and in particular make it evolve. So eta
Yes.
could also depend on t, is that right?
Yes, indeed. So actually, I did the result I will present is for a fixed eta, but then we'll see how to optimize eta, and then actually that we would like it to depend on t, and then you can use all the usual tricks like doubling trick to make it depend on t. So, but you're right. Actually, I did not mention eta until now. So actually the general regret bound. So I must say, because it was a tough but for me interesting discussion with the reviewers at ICML, I must say that the proof, well, as I said before, it's a special case of follow the regularized leader. So in some sense, this part of the paper was just like follow the proof, the analysis of follow the regularized leader in the general case, but actually with simply replacing the penalty by a phi divergence. It's almost that simple, apart from the fact that in all the references I gave before, follow the regularized leader is usually analyzed in the finite parameter set case. And some parts are absolutely trivial to extend, but for some parts you have to be slightly more careful. So still, it was not 100% trivial to extend the result. In the end, even to use it actually is not completely trivial, because you have the problem of this norm. Actually, you want that there is a norm on the set of measures on theta, such that first, this function that maps rho into the expectation of the loss when theta is drawn from rho is actually L Lipschitz with respect to the norm. But then actually you have another constraint. You want that your penalty is alpha strongly convex with respect to this norm. And if you do so, then actually you end up with the classical result on a follow the regularized leader. That is that you do as well as the best possible expectation plus this term eta L squared, the Lipschitz constant T over alpha, and plus the penalty over eta.
This is a norm on distributions.
It's a norm on actually not only on probability distribution, because it's not a vector space, but it's a norm on the set of measures over theta.
Okay, all right.
So like say for example the total variation norm. So I will provide examples in the next slide. Sorry, I was thinking about the next slide already. I will provide examples in the next slide. So importantly, like just if you, like in order to compute explicitly the upper bound, if you fix some rho and then you have the value of the divergence between rho and pi, then actually you can optimize with respect to eta. And you see that actually by taking eta in 1 over square root of capital T, that means that it would depend on the time horizon, then actually you obtain a regret bound in square root of T, which is as EWA. I will compare actually the results to the general results for EWA at some point, but of course you don't want to do it. Still actually, like the analysis, if you want to go beyond, is quite classical in the sense that you can just use the doubling trick, and then you would have a eta that becomes dependent on T, and then you're able to state a result for any capital T actually. So I will not insist on this. I would like to present the result because actually, well, first it's known actually that KL is one strongly convex with respect to the total variation norm. And so remember that you have two conditions here. So of course, if you want to make the second condition easy, you just have to take the norm very small. But then in this case, the first condition will become more difficult to satisfy. So there is, of course, an interplay between the two conditions. And well, it appears that in two examples, things match perfectly well. First, if you take the total variation norm, yeah, indeed, KL is one strongly convex with respect to the total variation norm, with respect as a function of rho. But then actually, if you consider like the function that must be Lipschitz, so it's the expectation of L, and then actually you just use Hölder's inequality, then you see that actually here, if you want to have the total variation norm, then here you have to bound the supremum of LT. And so basically you have to assume that the losses LT of theta are uniformly upper bounded. And indeed, if you go back to the reference, like for example, the book by Cesabianchi and Lugosi here, the result for the first result for EWA, say in the paper, is stated with like assume that the losses are uniformly bounded by a constant, and then they give the result. Okay, so here we need the same condition, and it's interesting to see that with the different proof, actually we recover exactly the same condition. Now, the result in the end, the corollary of the general result is just the usual regret bound for EWA, and it's exactly the same. Maybe here actually the constant is slightly worse. They have like eta L squared T over 8, I think. But apart from that, the bound is exactly the same. So in some sense, for now, we could just say that the general result I have is just able to reprove a result that was already known. So now let's have a look at the second example. And the second example is, as before, the chi-square. And here, actually, it's quite easy to see that the function x square is obviously too strongly convex, so strongly convex with parameter 2. And actually, if you just write it down and then you integrate with respect to pi, it gives immediately the condition that d phi, the chi-square divergence, is strongly convex with parameter equal to 2 with respect to the norm L2 of pi. Okay. The point is that then if you try to do things with respect to the norm L2 of pi, then you have to find like to check that this function, the expectation of LT with respect to rho is indeed Lipschitz with respect to rho, with respect to that L2 of P norm. But then actually the point is that here you use Cauchy-Schwarz inequality and the condition is slightly different. The condition becomes that LT of theta is square integrable with respect to pi. Okay, so the condition is less strong. Here, like you had the condition that LT of theta was uniformly bounded, and here it must be only square integrable with respect to the prior. However, of course, like the result is less good in this case because well, you have but still like it's more general. You have a more general condition, but you end up with the same result as before, but the KL is replaced by the chi-square divergence, which is like larger. So the bond is less tight, but once again, like under a more general assumption. So I think that here again, there is a similarity with the paper that we wrote, Benjamin, for Pack-based bound, in the sense that similarly, like using, even though the context was different and the form of the posterior was different, but like using other divergences, you make the bond worse. But on the other hand, you extend the scope of applicability of the results.
Nice to pay for generality, right?
Yes, yes. Yeah, I mean, like in this case, I try to apply this result to countable parameter space and then to continuous problems. Honestly, in the case of continuous problems, this chi-square really kills things, actually. It makes the regret huge. Still, in the countable case, where you have like LT of theta for theta, that can be just like indexed by the set of integers, then it can clearly be unbounded. And in this case, actually, the chi-square provides, I mean, the bound that I obtain are not so bad, actually. So it's, yeah, it's a price to pay for generality, but in some cases, it's less good than in others. So, yeah. Okay, so that's the end of the first part. And now I would like to switch to variational algorithms. That is the case where we will impose also some parametric constraints on the posterior. So maybe I will just provide a motivation for this, actually, Because like in the end, my objective was just not to derive nice formulas with gradients of tiled up everywhere, but also to implement Bayesian procedures. And in the team I work in, actually, they are like very into like trying to do with Bayesian principles things that are as efficient as when you're just using optimization tools. Okay, so the best possible, like the deepest possible neural network with as many layers as you want and state-of-the-art performances, but when you return a posterior and not only just a point prediction. And in this paper, MT and some other members of the team and other co-authors, actually, they indeed provided a variational approximation for Bayesian posterior in a neural network. And what's nice is that then actually you end up with not only a prediction for each image, but using the posterior distribution of, on the prediction, you can have uncertainty quantification and then classify the zones of the image where you are sure about your classification and those where you are not sure at all, actually. So practically, it seems to work. The point is that the online variational approximation that they use in the paper is nicely derived, but actually there is no, for now, there is no convergence guarantee, there is no regret bound. So our objective was to provide a theoretical analysis of this algorithm. And we are not able to do it. I'm going to tell you like, of course, it's quite a sophisticated algorithm. There are many things to study in it, but still we were able to study a kind of simplified version. So I will come back to the construction of the algorithm, the construction of the posterior. So this time we will restrict rho to belong to a fixed set. So I say Gaussians here. It can be something else. It can be slightly larger than Gaussians. It could be mixtures of Gaussians, or it can be, I don't know. But still, we constrain it to belong to a parametric family. And then we apply our generalized Bayes or FTRL strategy on this set, which means that now we don't minimize with respect to a whole probability distribution, but simply with respect to its parameters, which makes actually, it's good because in some sense we leave the infinite dimensional case to come back to the finite dimensional case. And obviously things will be easier to deal with in practice. So we propose to define the variational version of the previous algorithm like that. Okay. And like once again, you might not have an explicit form for this, but after a linearization, you end up with just an extension actually. So it's a kind of Bayesian version of the online gradient algorithm. Okay, so you minimize the scalar product between mu and the sum of the expected, the sum of the gradient of the expected losses plus your divergence between q mu and the prior pi. Okay. Still, actually, this definition was not, I mean, we took some discussion between Bader, MT, and myself, because it's not the only way actually to extend online gradient algorithm. And it appears that, for example, remember this definition for online gradient. So it's follow the regularized leader on linearized losses with a quadratic penalty. And indeed, if you differentiate this, you end up with the online gradient algorithm. But on the other hand, instead of taking the sum of the losses and taking the quadratic penalty, an alternative point of view is the kind of streaming point of view, where you just, it corresponds more to what you do actually in real life, in the implementation of the method. It's just that you only take the gradient of the last observed losses, but the penalty is this time not the quadratic norm with the distance to 0, but the distance to the previous parameter. Okay, so if you differentiate this formula, then you end up with exactly the same formula as if you differentiate this one. Now, the point is that, of course, when the penalty is no longer quadratic, then it's not true anymore. So in the beginning, I said, guys, let us replace the quadratic penalty by the Kullback in the first formula. And this gives what we had here. We call that SVA. And MT said, no, we should do it with this, like the second version. And you end up with another definition. That's this one, SVB. So you minimize the gradient between the parameter and the gradient of the expected last loss that you observed, plus the phi divergence between Q mu and Q mu t minus 1. The point is that...
Yeah, sorry. I was just wondering, this is an notation question, but Q mu t minus 1 is only the posteriori evaluated with the parameters that you had in the previous round, right? So
yes.
you're not, so this no longer depends on the previous rounds before that one. Is that right? So it only depends on t minus 1.
It does, exactly, in the sense that when you're doing online gradient, if I come back to the first slide, of course, where is the slide here? Of course, theta t depends only on the loss at time t minus 1, but it depends also on theta t minus 1, which itself depended on L t minus 2.
Right.
So like there's a recursion here. And exactly in the same way, in this Bayesian version, obviously what's nice with this formula is that you just do the computations using the current loss, but actually the previous losses are stored in ut minus 1. And it's even more important than that, is that if this algorithm is good, then it means that mu t minus 1 summarizes all the information on the previous losses that is important. So in some sense, if you choose well your variational approximation family, then mu should contain the relevant information.
Absolutely. It was very obvious for SVA, but maybe less for SVB, but yeah, thanks.
Yeah, because here, like, you still have all the losses in the sum. But yeah, actually here, the thing is that it's defined by recursion. So Q mu t minus 1 depends of LT minus 2, etc. Yeah.
Right.
So actually the point is, like, as I told you, like if you differentiate these two formula, you obtain exactly the same algorithm. For SVA and SVB, they look different. Maybe they are the same. So actually we tried it on examples. If you take Gaussian prior and Gaussian variational approximations, then it appears that the updates look kind of similar, but they are not exactly the same.
Right, can I ask a quick question again? On the last slide, I'm a bit confused how you're getting from a point theta to a parameter deciding a posterior mu.
It's not like here it was, for now we were just trying to design an algorithm, and then I will provide a theoretical study later.
Okay, so it's just analogous. It's not
right now it's just an analogy, actually. So of course it might very well be that what works for the quadratic norm doesn't work actually if you replace it by a phi divergence.
Okay,
actually we have some theoretical results for SVB, but only in some special cases. So sorry about that. Now, the thing is that still we compare these two algorithms in practice. And for example, here you see, like, I denote by G bar MT the gradients with so in case of, Gaussian distributions. This is the part of the gradient with respect to the mean parameters. G sigma is the gradient with respect to the variance parameters, assuming, a diagonal variance matrix. And then actually you see that in SVB, MT plus 1 is MT minus the gradient with respect to M times a constant, eta S squared. S is the variance of the prior, so it's a constant, actually. So in some sense, the update of the mean is exactly as in gradient descent. On the other hand, in SVB, MT plus 1 is MT minus eta sigma t squared, where sigma t is the current estimate of the variance times GMT bar, which actually was very exciting for me, because I was thinking, in this case, it means that maybe at some point we will be able to prove that SVB automatically chooses the right gradient step, because the right gradient step will be proportional to the variance of the current posterior. Well, we'll see. But anyway, the updates are not exactly the same. That's the take-home message. We wrote the updates in a few models, and indeed, like the algorithms are not defined exactly in the same way, and in practice, they are not. Sometimes they are different. Still, obviously, in this case, the theoretical analysis for SVA, for the first version, is purely a restatement of the existing result on follow the regularized leader. Like here, there was nothing to extend because it's already a finite dimensional setting. So just the existing results tell you that on the condition that the expected losses are L-Lipschitz and convex, with respect to the parameter of your variational approximation, then this will work. Still, this is maybe a condition that is not so easy to check. And another important point actually is that there is this very nice paper by Justin Domke where he proved that actually if L is a loss function and if Q mu is a parametric family, but where the parameter mu is actually a location scale parameter, then under very minimal assumption, you keep the convexity for the function mu gives the expectation of LT of theta. So it's very nice result, and quite surprisingly, apart from the Gaussian case where it's more or less direct, then actually as long as it's location scale family but not Gaussian, it's not direct at all. It's a very nice proof. And then the penalty has to be alpha strongly convex. So then here again, it's something that you have to check for each loss that you will lose. But actually then under this condition, and like for example, for Gaussian, if you use the KL, once again, like at least if the variance is lower bounded, then it's something that will remain true. Okay, and so in the end, you obtain the same kind of results. So this one is for SVA, sorry, just for the first version, I should have said. So the sum of the expected losses is as small as the best possible sum of the expected losses plus the remainder. That's always more or less the same here. The important point is that like this theorem, okay, I admit like this one, nothing new. This is just like the application of follow the regularized leader techniques to a special context. There was nothing new to do here. But what is nice is first that thanks to like Justin Domke paper, we know that the assumptions are indeed checked in some practical and relevant examples. And then also what's nice is that it provides a first analysis of online variational approximations, because these approximations or online variational approximations, as I mentioned before, they are used in practice, and until now there was no theoretical study for these algorithms. Okay, so in the paper actually we did, but maybe like it's getting late. Well, it's only getting late for me actually, but still, I don't want to start very scary derivations now. We fixed d phi as the KL, Q mu as a Gaussian, pi as a Gaussian, and then we computed all this explicitly and we minimized it with respect to our parameters. And then in the end, you can check that you have a regret of the order square root of t log t in this setting. For SVB, for the second one, actually, we were only able to analyze it in a very specific setting that is only KL and only Gaussian approximations. Then in this case, like we recover results that are quite similar to known results for gradients as well, in the sense that you obtain a regret in square root of t, and it's even a regret in log t in the case where the loss is strongly convex. Well, here again, like we were satisfied to have some theoretical analysis of online variational approximations. Once again, like we were not aware of such analysis before. What's a bit sad for now is that we are not really able to prove that the method takes really advantage of this adaptive variance for now. So it would be something that we'd like to do to show that, for example, like the method would be adaptive and identify here whether it's in this regime or not. But this is something that we're not able to prove yet. Okay. Just if I have 3 more minutes, Benjamin.
You do actually, exactly 3 minutes.
Okay, we did some simulations and on toy datasets and then on real datasets that were still toyish, but still they were real. Yes, like we tested many different methods, like OGA is the online gradient algorithm, and then we tested like SVA and SVB. One is in blue and the other is in purple. And you see that here, for example, SVA is extremely similar to online gradient algorithm, as in they are less good than SVB, that is in purple. We were wondering, like, will we observe this pattern on other simulations? And the answer is no. Like we use like one of the classical data sets of the machine learning repository, breast cancer data set. Well, in this case, you can see that SVB is the worst method, and SVA in blue is slightly better. In the end, we tested the algorithm on 6 or 7 data sets, and each time there was no conclusion, in the sense that an algorithm that is better than another on one data set became worse on another. So we were a bit worried that we would have no conclusion to draw from the simulation study. Well, it's not completely the case, because if you check here, there is this red curve, sorry, not red, green curve here below the purple one. So that the best method on this case, it's NGVI. It's something I did not mention before. And here, the best one is green, and it's NGVI. Once again, the thing I did not mention before. What is NGVI? I should say, actually, NGVI is the method that was used by MT Khan and his co-authors in this paper. It's his natural gradient variational inference. And the point with this NGVI algorithm is like it looks more or less like SVB, but it looks more or less like SVB using a different parametrization. And yeah, you know, like, of course, like gradient descent is not invariant by gradient, by a change of parametrization. And the point is that MT here found a parametrization that makes a lot of sense. But the problem is that this parametrization makes this assumption wrong here. Like it does not make this expectation convex as a function of mu, which means that we are not able to use the theoretical results. But still, in practice, MT told me like it's the best algorithm, and we implemented it, and we saw it like it seems to be the best. So at least it brings to a natural conclusion. That is that even though we had the first theoretical result on online variational inference, still we would like to have, well, first, of course, the analysis of SVB in the general case, but also this, like the analysis of NGVI. And I wrote here the update of NGVI exactly as it's written actually is in one of MT's paper. But once again, as I say, like it uses a parametrization that kills the convexity. That's a key in the analysis. So we were not able to apply our results directly. And I think it would be nice to find something for this method. That was 4 minutes, sorry, Benjamin. But thank you for, once again, for the invitation and for your attention.